Okay, we are online. Do you want to say hi?
Ni hao.
Hello, ni hao.
Sorry if you look sick, my room is really sick.
You're just a hypochondriac. Borderline Munchausen's. You should log on and become a viewer.
I've done that.
I know you have. You should do it again.
Why?
I don't know.
I'm already a viewer.
Because my life is extraordinarily mundane and I need to broadcast that to the world.
Can I just
QIA plus?
ever?
Dwayne is gone. Dwayne. Dwayne. I say 7 times.
We're just like
Dwayne. Come back to me, Dwayne. Dwayne, come back. You made us look good,
she was
Dwayne.
really sassy during Kim.
Right.
She had to call me.
Among the many things we will do today, we'll get your test back. You guys did rather well, I would say. I'm proud of you guys.
Not us. We're the
I don't think
rather.
anybody had a perfect paper. But what we'll do is we'll do test corrections. To prepare for the retake, you guys will take a piece of paper, attach it to the end of your test, and anything you got wrong, put the right answer and then an explanation why it's correct. For example, sometimes we have multiple choice ones, so just putting the letter isn't very helpful. But describe why it needs to be different. So we'll do that in a minute. The schedule has us doing the detector lab today. I know some of you, raise your hand if you started that last time. Anybody? Nobody? Okay. So basically you're going to take a whiteboard and you're going to use the little sonic rangers, the ultrasonic device that you've been using like for speed and position and stuff. And you're going to let it bounce off of you, and you're going to be sort of the human version of constant velocity or constant acceleration, positive and negative values, just to sort of internalize what those things represent. So anyway, that's the lab. Just a placard and one of those detectors, so maybe you can be doing it at once. So after test corrections, that's what I recommend doing. Now, that lab will be due on Saturday, so if you don't get it done today, you're a little behind. If you've got the help session on Wednesday, you've got Thursday's class, Friday's class. There is a quest due on Saturday. It pretty much, we covered last time the stuff that you would need for it. There's another quest posted, and I forget when the due date is. Sorry? Monday the 13th, thank you. Monday the 13th. And that has to do with now, if we were talking constant velocity before, now this is a different case, constant acceleration. And I want to spend a little time deriving the equations for them. We had our 3 definitions from last time, and we're going to add to them 2 equations today, and maybe a third one on Thursday. But in any event, then you'll be armed to do that assignment, which is due on Monday. Buggy Sparky, I plan to get you back on Thursday, and if I stay on that schedule, then your review will be due on Monday. So you've got that Thursday and that Monday, if anybody needs to questions for me. All right, let's start with a little review. What were the definitions we came up with for, say, displacement and average velocity, average acceleration, etc. Take a moment, look at your papers, maybe jostle the elbow of somebody else.
Wait, what?
Define
What were we supposed to define? It was probably the notes.
average velocity
Average velocity, wasn't that displacement?
and
versus
displacement.
change in time? And displacement is like how much it moved.
Yes.
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 From its original thing.
The change in x or the change in y?
Yes.
Yeah.
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 Hang
They're
on.
the same
Let me
document.
open up the chemistry packet.
Anybody
Wait,
want to
what?
give me one?
Then chemistry.
Not the packet. I mean the physics notes. You know what I mean? I mean the physics notes. Okay, well I can open them up too. We already did this, right? Okay,
Yeah,
but
yeah.
I think we're supposed to use like grammar words. Wait, did we get
Grammar?
average?
Okay, Vincent has the floor. Yes, you do.
Average velocity change in x final minus change in x initial. No wait, that's just change in x. And over.
So, what he's saying, there was two ways to write it, right? You could write it as the change in x over
Change in t.
the change in time, the elapsed time. And of course, if we were writing it out, then it will be the difference. And what's important is it's always final minus initial, right? When we were talking Chicago, New York, or Chicago, San Francisco, the order would make one positive and one negative, to say east versus west. And then, of course, T final minus T initial. I'm just going to go ahead and circle that final so that we keep final and initial. Now, at times we might say it's x2 minus x1. There's a lot of different ways to say it, but for now I'll put F and I in final minus initial. All right, he did some heavy lifting there. What's an easy one based on what he's already told us? We go up on that. Jack, you want to take a, sorry, Jack, you want to take a shot at it?
Which one?
He's already kind of told us what this is, right?
The change in x? Isn't
Yeah.
it like your initial, the final minus the initial?
Right, we had already had that from the numerator. So we'll write that down again. Final minus initial. And if this was average velocity, now we have a special name for this. Do you remember, Tara? Displacement. Okay, your hand is up. You got the third one for us? There we go. Those were our three equations, but we also said we can go one step further and call them definitions if we want. But mathematically, that's going to work the exact same way as a nuclear sign. Okay, and we said, okay, these seem reasonable. We have plausible names and everything. But to be careful, these are not the same as speed. These are not the same as distance. How would you alternatively define those? He says, could we for speed take the absolute value of velocity? So we just get rid of that sign. So when we did Chicago, New York, sure. Just get rid of the sign. We would turn around and go New York to Chicago. That's fine too. We could get rid of the sign. Does this break down anywhere, Bert?
We change displacement to
I have to do what?
displacement instead of distance.
So we'll say this is true sometimes, but it's going to fail, Timothy, if we change direction. Remember, Chicago, New York, Chicago was zero displacement, zero velocity, and of course our speed was never zero. So we have to be careful. But what we could say is it is distance over time. And so this has no direction, no sign. If you change direction, you just keep adding up. You know, you go to New York, you have a number, you double back, you just keep adding to that number. For example, the wear on your tires. It's not like you go east and you wear them, you go west and it builds it back on, right? That's going to be based on the total distance. What about, well, we've also defined kind of what distance was. So we have distance, and now we have speed. All right. Is everybody comfortable with that, sort of? Starters? You guys look horribly bored. You ready for some new stuff then? Okay. So now we want to do the special case. These are always true. Now we want the special case of constant acceleration. What would a graph of velocity versus time look like with constant acceleration? So here's velocity versus time. Did you say a straight line? You like that straight line? And it's a constant acceleration of 0. So it's kind of unexciting. Okay, so that was constant acceleration. This is constant acceleration. Say 8 equals 0.75, like that, meters per second squared. Is this constant acceleration? What do you guys think? Okay. Good. So this might be A equals negative 0.75 meters per second squared. All right. What kind of graph would not be constant acceleration?
When it's curved, when velocity times the curve.
So that would not be. This would not be. But any straight line, be it horizontal or inclined up or inclined down, is fine. Were we talking average or instantaneous here? Yes, because every moment we look is different. So we'll call this instantaneous. How would you go about finding the average if you were given a graph like this? Take a moment and talk to the people.
What? We have to talk about how we find an average velocity when we're given a graph like that.
When looking at a graph, like what?
The curved one.
Curved? Isn't it just not constant? Because it's exponential. Oh, like linear? Okay. Okay. Isn't it the slope? I feel like it's the slope. Is it the slope?
Slope would be the acceleration.
Yeah. So if it remains constant, it's a linear graph, and so you'd find that constant.
Yeah.
You do not sound very confident in your answer.
Do I ever sound confident in my answers?
Yes.
No, I do not, except for that one. Okay, but how would you find the slope of a line that would be like this?
That's not constant acceleration, therefore it has no slope.
I said average, and it said straight line.
Add up all of the velocities. Okay. With a line, how many points are there in the line? So you want to do that now? Okay. Assuming your data isn't too noisy, and it really does fit a line, exactly how many would you need? 5, 10, 20? Yeah, I'm saying this is like super good data. Better than anything we'll actually physically collect. It looks like a nice flat line. Okay. So as long as we truly are the line and we don't have to worry about noise, he says, go ahead, grab 2 points, and now what will you do with them? let's say this was 20, and this one was 10. Not sure what to do with them? Take a moment. What can you do with those 2 points to find the average value?
So why?
I think I know where he's heading. I think he was heading towards slope. But ask you something, we really need to figure that out.
Joshua.
Do you have an idea?
Wouldn't it just be doing the slope, finding the change in x and y?
So, all right, let's do that. Find the slope. So you can say we'll do the rise over the run.
Yeah.
Right? So delta V over delta T, and so let's make up some times. Let's say this is 2, and this is 12, and so you want to take 20 minus 10?
Yeah. If those are the
Minus
numbers
10,
there.
Of course, those were meters per second. And we'll divide by 12 minus 2, and of course that was seconds in time. So this is going to be 10 over 10, which is 1. What do our units look like?
Meters per second squared. Meters per second per
Is that
second.
average velocity?
No.
Meters per second squared. What is
No,
that?
meters per second per second.
Acceleration.
Okay. So really what we've done, and what you did was useful. It wasn't just what we were looking for at the moment, but maybe this is where he had been going before. Kind of think about it. What have we found?
Acceleration.
Okay. So we could call this our average acceleration. We can do that because it's constant. It didn't matter any 2 points we chose them, we'd get exactly the same slope. We would get the acceleration. Okay. But let's go back. So that was useful, but really, we didn't do anything new, right? We just took our 2 points, we defined an interval, took our 2 points, found average acceleration. We're still looking for average velocity when we're given a whole range. Okay, so position. I'll say this, we're going to go there, but we're going to take our time because that's a little bit tougher. I like how you were thinking. But if I said, okay, you start at 10, you end at 20, and you constantly increase, do you have a gut feeling for what that average, that kind of middle value would be? There we go. So we'll just add any 2 points together. Sorry. We need for the interval, right? So we'll take what we take to be our final, we'll add to it our initial, and we'll divide by 2. And so 20 plus 10 is 30, divide by 2, and of course we get the value right in the middle, we get 15. So that kind of makes sense, right? Diane, does that make sense? Okay. I start at 10, I end at 20. I'm going to say that value right in the middle, 15, was our average. Okay? Now, is there a circumstance where that would not be true? Because you'll probably want to use this, and you'll probably want to use it where you shouldn't. So take a moment. When will this fail? When will the value, the average, not be the one right in the middle? Talk to your table mates. Make sure everybody's kind of on the same page here.
When it's curved.
I don't think constant velocity can be curved.
Oh, it's constant. I don't know. I have no idea.
It's like going at the same time, but if it's curved, it's like going exponentially.
We're finding acceleration.
Same. I was like, oh,
How dare you?
you sure it's italics?
I am.
What do you guys think? Will this always be true, or can you think of a circumstance in which it would play out? Bert?
There's not constant acceleration.
Okay. He's saying, if this was a line, it would always be true, but you have anything other than a straight line, you can't pick the value halfway between. It doesn't work. But for the straight line, the constant acceleration case, it will always be true. So we have those three definition equations, always true. Here's the sometimes true. And it is when acceleration is constant. So we've added a fourth equation, but you can't use it all the time. You can use it for constant acceleration. Now, Emily was heading off in an interesting direction, and I think it's where we were originally going when we were looking at the slope. So let's plot some things. Let's say we have constant velocity, and we have constant acceleration. And I want to plot a whole bunch of stuff now. I want to plot position versus time. I want to plot velocity versus time, which we kind of did, but we're going to do 6 of these now. We've only plotted 1. And then I want to plot acceleration versus time. And I want to do it once for a constant velocity case. I want to do it again for a constant acceleration case. So, if the people at your table, you guys maybe want some whiteboards for this? Yeah. Well,
I would like a reason to
I want you
live.
to kind of flesh out what these graphs might look like. Okay. So, you guys have a board? Marker? You guys have a board. I'll come back with whiteboards and markers.
I would like a reason to live.
Wait, what?
Hello, my name is Tag, and I would like a reason to live. Joshua Wilder. Joshua Wilder.
You said I could have it for the week though, because I don't have one.
I know, but I want to touch it. Let me touch my pen. Please. Just let me touch it.
What the shit?
Let me touch my pen. This is actually one Lashes pencil I stole before she came to class.
Today?
Yes.
It's for you guys.
Oh wow, this is where did I go wrong? Flashbacks to around February 1st last year. In the okay, we should start thinking.
Thank you.
Okay, wait.
Go ahead, grab it.
So,
See, I thought you guys were going to get to the first one.
Wow, those are terrible.
the X.
My grandmother could do better.
Your grandmother is awesome, okay?
So you need
Thank you.
I don't even know where he's going with this. Like, what am I doing with my life?
Advocate,
Just give me, I mean, that would be kind of cool
What would be kind of cool?
if he just gave us that. Oi.
We could literally just look it up, Kat.
I feel like shit everyone but us was doing. Okay.
Okay, what are we supposed to do? Oh, okay.
Find out what the graphs are.
Yes.
So constant acceleration.
Give me the
Is
pencil. No, not necessarily. Stop it.
Hoi.
Stop.
Hoi.
You're wrong.
Hoi.
You're wrong.
Hoi.
Give me the marker.
Hoi.
No. Shame.
Ow.
Stop.
I'm bleeding.
Constant velocity.
I'm bleeding.
Meanwhile, can you guys do it on stretch paper?
Velocity.
You get somewhere.
Shut up. Oh
Can
my
I
god,
erase
these are
it?
terrible. What is wrong with you?
I wanna erase it.
These are not legible. Okay, go ahead. This is why he doesn't like us. Jacqueline. Hey. Stop.
Hog.
Oh my god, go fast.
Hogging everything.
You're honking the board. Okay, now stop. Go away. Move your arm.
Look,
Jacqueline,
that's what people do.
Jacqueline, we're gonna get in trouble.
He left. He left us, Eden. He left you. He left us, Lord Shield. You know what that means? You
Stop.
scared him off.
Stop that.
Why is it
Jacqueline.
so weird?
Jacqueline, stop. Jacqueline,
What if we just
this is why no one
all
likes
the
us.
title
Oh my god.
and then made it all Comic Sans?
Why?
Oh, the shield.
Okay. Stop it.
It's not straight though.
Leave it alone.
But then it's not comic.
Accept it as it is. Don't be hopeless.
So that means it's linear, right?
Because it's a change in X over a change in Y.
Yeah.
But if the change in X over the change in time is always the same, shouldn't it be this? Because it needs to be the same for it to be a constant velocity.
The change in X over the change in Y? No. Right?
Because it needs to be the same every time.
No.
Yeah.
I don't think I think it would be like.
I think you're wrong.
I think you're wrong.
I think you're wrong.
Okay, so this is the constant velocity, right?
Yes.
And what's the X?
X is position.
Well, wouldn't position just keep going? Because you're going more position every time. Boy.
Because you're going more position every time. Jesus Christ.
It's not like the position is really insane.
Jacqueline?
Yes.
Our teachers are going to find this video one day.
Oh, I forgot. I was on video.
You're not helping your cause. So,
We're focusing on this.
okay, whatever. So, since it's X over T, shouldn't it always be the same?
No.
Okay, I trust you.
Yeah.
I trust you.
You should
Oh,
trust
because
me.
it's the change.
Yeah.
Oh,
The change is constant, not the line. It's not always going to be the same because
I
that's
get
how
that.
physics works. Do you understand? No. Don't be wrong. Okay.
okay.
What's the next one? Okay. So the time keeps going, so we know it's going to be a line,
And the
right?
velocity is the same because it's constant. So
I like how they're literally the exact same graph. Wait, no.
No.
No. Oh, yeah. Wait.
yes, because the
Wait.
velocity is the same. and
Wait.
so is
hold
the
up.
time.
Hold up. Oh, that's velocity. Okay.
Yes.
I got you. Wait.
Yes.
Yes.
Yeah.
Yes.
Yeah.
Yes.
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 I know.
Fine.
That's what I said in the first place, and you disagreed with me.
This one's also going to be like that.
What's acceleration over
Yeah,
time?
because it keeps accelerating. And that means, what is this? T is what? Time? What is time? Time is a construct.
Oh my god, stop.
Okay. So, the acceleration is always the same. Oh, no, it's not. No, because this is the velocity one, right?
Yeah, it's constant velocity.
What did you do like you were talking?
What did I do? Oh my god.
So the time is going to keep going, right?
Yes.
Okay, so that means if there was no acceleration, it would just be one. But the acceleration changes.
Does it?
Yes.
In a constant velocity,
It's
does
not-
the acceleration change?
Okay, let's hear some ideas.
We haven't even finished the first.
So which of these 6 did we already draw?
First two.
We did a velocity versus time for which case? Constant acceleration. All right. So we'll draw like the simplest one we can. There we go. All right. If we were... All right. Tell me another one.
Acceleration time for constant acceleration is just a horizontal line.
There we go. Somebody give me another one.
Acceleration for constant velocity is just 0.
Okay. All right. Let me give you another one. Two volunteers, perhaps. Grant, are you involved?
So for constant A, maybe parabola.
So we're curving. We're up or down? Up. All right. So if we were to use as our reference, say, the identity line, we're going to deviate from that. We're going to curve upward. Sorry, you said there was a special name? Parabolic. give you another. Emily. Somewhere. All right, how about there? One to go. What would that last one look like? Yes. Straight line. Okay. So now, from our formulas, we found a way to go, right, when we were fooling around trying to find an average value, we accidentally figured out what first before we went back and found the average velocity. What did we do by accident first? Yes. We found the acceleration, and how did we do that? So if we take the slope of this, we should get that. Did we just happen upon it the one time we can do it, or is it more general than that? Can we say, looking at a graph, if we know the slope, we can always find the other graph? What's the pattern here? What one can we look at and say the slope must be this other graph?
The slope of displacement velocity.
So you're saying we start here, take the slope, we get velocity. We start here, take the slope, we get acceleration. That seems to work. This slope is always the same, so we get a straight line. This slope, what's happening to this slope? Is it constant? It's increasing, right? Oh, and this just happens to be increasing too. All right. Does that only work for constant acceleration? Seems to work for our other example too, right? The slope of this is 0. That's what we get. The slope of this is a constant. That's what we get. All right. So it seems to work everywhere. You can go to the next, to the right, basically, by doing slope. Now, do you suppose there's... Yeah, the slope is the incline, right? And we can use our formula too. If the slope of this were 2, then we need this value to be 2 all the time.
So then how do you find the slope from the quadratic?
With some difficulty. So the ones that we choose to be quantitative with, we're going to choose these examples. Okay. The quadratic, we will build that. Right now, I'm happy that you see that the slope keeps changing and going up, which justifies this. We aren't going to try to put a number on this. What about going the other way? What if I gave you acceleration graphs? Could you generate velocity? If I gave you velocity graphs, could you generate position? Is there something kind of like the opposite operation of taking slope that took us to the right that might now take us to the left? Take a moment, talk to the people at your table. See if you can come up with what operation that would be.
So he's saying like if you take the slope of something, is there something that will like, so we took the slope to get the acceleration, right? Mm-hmm. Is there something we can like take out of the acceleration to get whatever we started with? So like,
I'm assuming so, but it seems like we can't think of it.
just like take the
You can
slope.
do it without using those.
Like if you had
Could you
a
know?
Find, like, could we find this using this?
Can I
Like-
borrow your bright? Oh, you're still using it. Can I use somebody?
like wait. So if they gave you like a point and
All right,
If they give
who's
you-
got an idea? How could we go the other direction if you had acceleration graph that allow you to generate the velocity, or if you were given the velocity, you could generate position? Who's got an idea? Over here, I was hearing some scary words. Should we use those scary words? So if you know calculus, you would recognize taking the slope, moving to the right is taking derivatives. But I'll seed that idea. Derivatives take you to the right. What would take you to the left? Antiderivative. We might call them Integrals. Now, but we don't want to use those scary terms because not everybody's in that yet. What is that related to in terms of geometry? If you take a derivative, what are you really doing? Oh, sorry, an integral.
If you're taking the antiderivative, you're basically just finding the area under the curve. So basically the area from the x-axis to where your line is.
Okay, let's do that. Let's look at the areas. Okay, so if I take this graph here and say, okay, after 1 second, I've got that much area. After 2 seconds, now I've got that much area total, right? Twice as much. 3 seconds, now I've got 3 times as much. That looks to me like these values, 1, 2, and 3 times the first one. That does seem to work. Let's keep going. If I were to go here and try to go that way, does, at least qualitatively, does this look like the right process? That the first second we add a little bit. Second we add more than we did the first. And the third, it's like almost as much as all that together. So instead of going up on even increments, the second one was more than the first by itself, and the third one altogether more. So at least we justified that shape, that curving upward. All right? Now, will this work everywhere? Can we use it on that first set? Do we go here and say, after 1 second, I've got that much. After 2, oh, look at that, it's twice as much. After 3, and again, 3 times. So that seems to work fine. Any problems? How do I get velocity from acceleration?
Well, you don't know where like the velocity starts, so if you know like you know the increase.
Okay. He's saying if we start at the origin, and look at these, we were always starting at the origin, we were okay. But if we're not starting at the origin, all this does is tell us how much more we add to it. And we lost a little information. We didn't know that we would displace up a little bit. So going this way works to a point, right? It will work if you're starting at the origin for these others, but if you're starting somewhere else, it's going to only tell you how it changes. So there is a limit on it. Okay. And when you look very uncomfortable, we'll let that simmer for a minute. We'll pick up with this next time, but I want to use a combination of these two. I said we were going to have 6 formulas, right? We started with our 3 definitions from last time. We derived our 4th one. I want to lay out the foundations for our 5th one. And whereas I told you we're going to stick to the easy stuff, this is a little more complicated. So let's go to this one. And we'll say our example is constant acceleration. And we have a velocity curve, velocity versus time. And it's going to look like this. We're going to start at some value that is not 0. And we're going to increase. So this is V final up here. This is the initial. And I want to generate from it, not even that, I want to know what is the displacement that happens on this time interval. And they're going to go from here to here. But what I want you to use is this idea, using the area, right? The area to generate, say, a position graph, or in this case, a displacement amount, a value. You've got to build that 5th equation that you can use over and over again. It'll probably be the most used equation you're going to have. And my hint is, we said if we looked at this area, we should be able to say something about displacement, the change in position. So to make things a little bit easier, I'm going to divide it up into a rectangle and a triangle. So we don't need calculus. We just need some geometry. Rectangle, the area of a rectangle, the area of a triangle. And I want you to use those to see if you could put together what my value of displacement should be. Talk to each other for a second. So you at least try out those formulas and see what you can write.
I should probably make this wide. But wouldn't it be like you already have this or whatever, and then as you go you're gaining more? So wouldn't it be like, so basically you're trying to figure out what the distance of this is, and that's your displacement?
I don't understand. What are you saying?
What? He said we're supposed to like use the triangle.
Yes, I got that.
Oh,
But you're not
obsessed.
Sorry.
Yeah. So you start off here, and as you go,
Okay, but let me see what displacement is.
How about rectangle?
Displacement.
Rectangle.
That's a change. So it's displacement, just the distance gone. You went?
yes. So we already know this, right? The initial times.
You'll look a little bit different. First off, if we were going to say displacement, our change in position is related to area, how many geometric areas do we have to add up? 2. All right. So the first thing we're going to do is take the area of the rectangle, and then we're going to add to it the area of the triangle. Okay. Who's got the formula, the generic formula for a rectangle? Base times height. Okay. Now, what is our base here? Our base is going to be our elapsed time. So we can say delta t is the base. What is our height of the rectangle? Our starting velocity. So we'll say vi times delta t is the first contribution to our displacement, our change of position. Now, do the units work out? Yeah, this was in meters. And here we're going to multiply meters per second times seconds. So we've got meters equals meters. All right, let's keep going. What's the formula for triangle? Base times height times. All right, so let's do that. 1/2. Now, the base, that's still delta t. What's the height? So the difference between these. So for the time being, I'll say delta v. Okay. And this is indeed one version of the formula. And we say meters per second times seconds is meters. And now the one thing that's hard is units will not tell you if you're remembering or forgetting constant on the time. But here's the thing, because we call it a triangle, rectangle, that's why you should be thinking, oh, factor of a half. A lot of students forget that. Now, we're going to see this and use it in a slightly different form. Like if you go on the physics classroom or look in the book, you're going to usually see this written V naught t plus 1/2 AT squared. We get from here to there, but maybe it's not obvious how. Take a moment to talk to each other. Are there some substitutions that we can make that will take us from what we derived, which is correct, to the more common form that you're going to see it in? Talk to each other.
What?
so this is what we have to get to, or is this what we have?
This is what we need to get to.
Okay, what do we have over here?
And then these are just the ones we don't really need them.
Boy. Okay, can we erase this giant rectangle thing?
No, don't. That's what this is still applying to.
Okay. Change the T. So V initial, but this means okay.
Okay, how can we get from what we derived to the version you usually see that I put the box in? The first term is a little bit easier to see. What have we done with the first term? It's pretty straightforward. We wrote VI delta T, and now we've got V naught, V sub 0 times T. How did we do that? Cheap.
If you do left side to the right side by delta T over delta T, which is 1, then you can just left right the delta T over delta T times delta T times delta T, and then the delta T over delta T will do the same consolidation, so there's A, and then you have T times T.
You did the second term, the harder issue. I thought we were focusing on that. But all right. She says you can get this by multiplication. I was thinking substitution. Maybe we're both getting there by the same means. What I was going to ask, did we have a formula that had delta V in it before? Okay. And so we had this formula, A naught equals delta V over delta T, and she says, now if we just cross multiply, delta V equals A average delta T, and substitute that in, now we get something that essentially looks like that. We would still have 1/2 A bar delta T squared. But to get from there to here is a lot easier. Okay? But did you see with the substitution how we can get rid of delta V and end up with just acceleration? Yes? Okay. So the delta T and the naught, that's just a naming convention. Okay? And what we can do is say for V's, we said V initial, V final. We could have called them 1 and 2. And really what is going to be popular is to call this V naught, and the other one, any other V that you were considering. So they're going to call it V naught, and V is going to be basically our initial and final. And so initial just became V naught. Now, dropping the delta T from T, when would they be different? Right, so if you were using like ticker tapes, you could have used the 0 point. But the assumption in our formulas here is that you're able to change the plot. You can always start at 0. And then when that's the case, the delta T is always just implied that you started at 0. And so this is whatever your last time. And so we just made that substitution. So as long as you're careful and don't start at like time equals 2 seconds or something, you'll be fine. All right. People feel reasonably comfortable with that formula? You know where it came from? This is the rectangle, this is the triangle. We're going to remember the factor by half by the triangle. What gets hard is when you go from this to this, you remember the square. That's the other thing that people forget. I don't have a good idea for helping you remember that. This is probably one time you just got to throw it in. Questions? Okay, yes.
I can understand how you get like the area and then the change in there.
Okay. So if we march along at constant value, every second we add the same amount of area. So if this number were 2, then we add 2 more. And 2 more. So as we add up, we get 2, 4, 6. And all that we're doing is plotting here. 2, 4, and 6. This area gave us how this was changing. Okay? And now the same thing here. If we took and added these areas together, This, of course, being the biggest area, not even. So now this one is going to be the biggest jump. That's why we are curving up. When we left the identity or the whatever straight line, we would have been on 0. Okay? And this works here. The only place we ran into trouble is when we were going to a place that didn't start at 0. Okay? And so we kind of said this general idea is going to work, but we aren't going to call this the area position. That's why we made this special displacement to say only how that was changing. So we kind of got rid of that problem with starting at 0 or not. So you are taking a little bit of faith there. But he said I can connect this with that. The area idea was pretty good, worked most of the time. And because I did this instead of saying it was the area under the position curve, now I'm saying calling it the displacement, the change. Okay? All right, now I know that was a little hard to swallow. It's going to take some practice, and believe me, we'll give you lots of time. But right now, let's do exam corrections. A couple people made just tiny, tiny little slip-ups, like, as an example, like moving a decimal place, or you left off the unit or something. So, those are called fixes. And what you do is you just come up and sit here by yourself and rework that little issue with your problem on your own. Not talking to anybody, not looking at your notes or books. And then you give it back to me and I grade it as though you did it on the day of the exam. All the other ones, you're just making a correction on a sheet of paper at the back. Now you don't actually write on the test, do everything on a sheet at the back. But at the top, if you have any fixes, list fix, give them to me, and then if you're doing the rest, just put corrections and work on them and make sure you've got your name and the staplers in the back. Okay, in no particular order. Jack, you've got a couple of fixes. Why don't you come and park yourself here? Tyrone, there are a couple of yours. Emily, you have a fix. So why don't you come and sit here? Eden, you have 2 fixes. Why don't you come and sit here? Bert, you have just corrections. Zoe, Alex, looks like just corrections. Timothy, just corrections. Ayush, corrections. Lucian, just corrections. Taylor, you have a fix. Why don't you come and sit here? Rob, corrections. Theo, corrections. Josh, corrections. Henry, you have corrections. Amit, corrections. Grant, you have a fix. So why don't you move on up here. Vincent, you have a fix. Actually, I guess you can kind of stay put.
Are they doing it on the back sheet or are they doing it on the separate?
Yes, again, make no alterations to the test. Put a sheet of notebook paper on the back, put on the top whether you're doing fixes or corrections. But please do not make any changes to the test. Dwayne is absent. Diane. You have corrections. And Eunice, you have like 2 fixes. Again, no separate these papers. Yes. Separate piece of paper for fixes, separate piece of paper for corrections. And then go ahead and staple that on and do your corrections. So, for example, well, whatever you need, just say I couldn't tell, it looked like we had two things superimposed on each other. Right, I couldn't tell if that was, we wrote a T over it, or if we have G's on the top. So tell me what force you're talking about. When you were talking about original forces and stuff. Asking the two specific most of it was correct. So if she's falling, at the moment that she's reversing direction, that's a shift. It's a correction, but it's not make sure in case you get separated.
Even if the mass of the kickball is too low, Joanne will still have it'll still be for the people. It's like there's still friction. Even if the mass is going too low, if there's there's enough force, there's still force pushing you can do that. So that's not the reason. The mass of the kickball would have to be zero. That's to explain.
Once you've done your fix or fixes, show me. I'll give you credit, and then you can go and do your corrections. As in inertia. We're not talking, you are correct, we're not talking specifically about what is achieved as a whole.
done this on their smooth surface. And now she responded to it. There is a So, what does the application say she's got kids and she's So that's the difference between existing, which means small, or being able to negate it. You got a fix for me? Good. That. You got one that's what we're doing is we're starting 5% Are you ready for me to check, or do you need to call your phone? Sure. You ready for me to score one way or the other?
Made me fix 2 more because I wrote it weird. I had to put meters per second squared, and then over here I put 55K.
What kilograms per second squared?
So yeah, that's me.
And I put a fraction instead of this.
So we have to, for the corrections, we have to like correct them and then say why they were wrong.
We do. I think we just correct them.
No, I think you have to say they're wrong.
No.
Why they're wrong.
I don't think so.
For fixes, I don't think you have to say why.
With the corrections?
No.
Okay. If you're not doing a fix, if you're doing corrections, it's perfectly reasonable to talk to other people because you're not getting additional credit. You're just learning about your mistake. Doing that with others is probably helpful.
How'd you do number 5? You got it wrong too. Okay. How about,
I got half credit actually.
what'd you get for number 8? What'd you got? That's
Number
proper
8?
grammar.
I got A, I think. Did I get
That's
that one?
wrong. Yeah, it's
What?
wrong.
Why is that wrong?
Because
That was weird. I didn't think any of them were particularly correct.
it's like because the ground isn't slippery. I don't.
Doesn't she actually like move a little bit? That's what I thought. It was just that her mass was too.
Like LOL.
B?
Like if it was ice, she would like go back.
Yeah.
Yeah.
It's just the friction. Or
lack
whatever.
thereof. Right. So
But none of them actually say that. So I was like, oh yeah, it's A because like it doesn't generate enough force for her to work against. I did not get that one. Do you want to ask him?
no.
We should.